When we talk about the maximum wavelength of light with sufficient energy to power a chemical reaction, it's really important to point out that just because a certain wavelength of light has energy greater than the enthalpy of reaction does not mean that shining that wavelength of light will necessarily produce the desired chemical reaction. Another way of writing this here is just that if we have a photon with energy that's greater than the enthalpy of reaction, that doesn't necessarily equal a photochemical reaction occurring. And there's a couple of reasons why this might be the case, but we can illustrate those, or at least one of them, very simply with an example. So if I show ozone here decomposing to form oxygen gas and then atomic oxygen, the enthalpy for this reaction is actually quite low, only 105 kilojoules per mole. And so if I calculated the maximum wavelength of light that would have sufficient energy to drive that reaction, I would come out with a wavelength of 1139 nanometers. This is out in the IR region of the spectrum, so we're not even in the visible region anymore. And so this is fairly low energy light, very long wavelength. And if you look at this and say, okay, well, that's all the way out in the IR, so anything lower than that should have sufficient energy to drive this reaction. So if I simply took a blue photon using maybe a blue laser pointer and shown it on ozone, that should easily drive this reaction because it's got 272 kilojoules per mole for the photon's energy. But if you do this, it doesn't work. It doesn't happen. We don't drive the cleavage of ozone to O2 and atomic oxygen. The reason for that has to do with the absorption spectrum. If we look back at this absorption spectrum for O3, what we see is that it absorbs maximally around 255 nanometers, and then it drops off all the way to essentially 0 above 300, maybe above 320 or so. And I haven't shown the whole spectrum, should have shown it farther out, but essentially at 440 nanometers, there's basically no absorption by ozone whatsoever. So you can shine all of the blue photons on it that you want, but if it doesn't absorb any of those photons, then the energy isn't transferred and no reaction can occur. So the number one rule with any photochemical reaction, that's a reaction that's driven by absorption of light, is that you must have absorption of that light. If there's no absorption at the wavelength that you're shining light at, then nothing will occur. There's other reasons, though, why just shining a light that has sufficient energy may not produce the desired photochemical reaction. And that's because after absorbing the photon of light, there are multiple other pathways that the molecule can go down, or multiple other ways that it can release the extra energy that you've put into the system. So we can look at that here briefly. If M is simply my generic molecule, then if you shine light on it, it absorbs a photon of light. That extra energy then promotes an electron, right? If you remember from general chemistry, it promotes an electron from ground state energy orbitals, its ground state, promotes an electron to some higher energy orbital, and that's termed then an excited state. The molecule has that extra energy, an electron is promoted to a higher energy orbital, and we're in an excited state. But that excited state can then undergo a variety of options. So first, it could undergo a chemical reaction. Yay, you know, we powered some chemical reaction that occurs from that excited state, unless it's not the chemical reaction that you want. And there are many cases where you can have multiple different chemical reactions that occur, and it may depend on the particular excited state that you're in. So if you think about an excited state as being a case where an electron has been promoted to a higher energy orbital, well, there are many higher energy orbitals. So depending on where that electron gets promoted to, it is possible sometimes to have multiple different reactions that occur. Sometimes even from the same excited state, you could have different reactions that could occur from there. Additionally, in addition to chemical reaction, however, there's also the possibility that the electron just jumps back down to the ground state and releases that extra energy as a photon of light. That's primarily what we talked about in General Chemistry 1. And depending on the particular excited state, we refer to this as fluorescence. There's also phosphorescence. Essentially, just we sometimes lump it all together and call it luminescence. And in this case here, we've just given up the extra energy that was absorbed by giving it off as a photon. Now, it's important to point out that the photon that's released will always be of a longer wavelength and thus a lower energy than the original photon that the molecule absorbed, because some of that energy is lost through molecular rearrangements. And often, even if you promoted an electron to a higher energy orbital, it might jump down a few energy levels before it releases, before it jumps all the way down and releases a photon of light. And so the photon that gets absorbed is always going to be longer than the longer wavelength than the original photon. In addition to both of these processes, it's also possible for the molecule to simply dissipate the excess energy, not by giving off a photon, but simply by doing molecular rearrangements that involve the loss of that energy as heat. So sometimes that extra energy is simply lost in a thermo sense, just by the loss of heat. So since all three of these are possibilities, then we can see that simply absorbing a photon that may have sufficient energy to power a chemical reaction does not mean that a chemical reaction or the desired chemical reaction will occur in every single case. And that leads us to another concept that's known as quantum yield. It's given the Greek symbol phi here. And quantum yield is simply the number of molecules that react as desired, divided by the total number of photons that are absorbed. So for example, if you had 1 mole of a substance and you've shown 1 mole of photons on it and all of them were absorbed. Let's say that only, say, 0.2 moles of that actually ended up going on to react in the desired way, then your quantum yield would be only 0.2. Let's do a couple problems that might help solidify some of these concepts. So in this first case, we have an absorption spectrum for a hypothetical molecule as shown here in this graph, and dissociation of this molecule, so undergoing some chemical reaction where it breaks apart, that requires 265 kilojoules per mole of energy. So which of the following wavelengths of light might cause dissociation of the molecule? The first thing we have to do is just figure out, okay, what's the maximum wavelength of light that has sufficient energy, even regardless of whether the molecule absorbs that wavelength. So we'll just do what we've done in the past. Lambda is equal to 119,627 kilojoules nanometers per mole divided by 265 kilojoules per mole. And if we simply plug that in, 119,627 divided by 265, we come out with, it looks like 451 nanometers. 451 nanometers. That's the maximum wavelength of light that has sufficient energy to drive a reaction. And so right away we can say, well, 600, which is out here, and 550, which is right here, those are both longer than the maximum wavelength of light that has the sufficient energy, so it can't be A or B. So 450 looks attractive because it does have sufficient energy, but if I look in my spectrum, there's essentially no absorption by the molecule at 450. So 450 is not going to be a good wavelength to drive this reaction because the molecule doesn't absorb at that wavelength. So really the only option is going to be 400 of the options I've been given. Of course, there's other options, but 400, the molecule does absorb, maybe not a ton. It's got an absorption of 0.2 at that wavelength. So maybe not a ton, but it does absorb. It certainly does absorb at that wavelength. And so 400 would really be the wavelength of those four options where where we would expect to see, or at least hope to see, dissociation of the molecule by absorption of that light. We certainly don't know that it would. We would have to look at the quantum yield, etc., and the other processes that could occur, but at least this one of the four options has the best chance. Second molecule, or second example here, is reaction here. So we've got propionaldehyde, which is shown decomposing to form ethane and carbon monoxide. And it does so upon absorption of 302 nanometer light. So what's the quantum yield of this reaction if we produce 1.03 times 10 to the minus 3 moles of CO from absorption of 1.91 times 10 to the minus 3 moles of 302 nanometer photons by propionaldehyde? First thing we have to do is just write out the reaction and figure out the relationship between, the molar relationship between CO and propionaldehyde, since propionaldehyde is what's actually absorbing the light. So we can draw out the chemical reaction, CH3, CH2, CHO, going to CH3, CH3 plus CO. And it turns out that the reaction is balanced just like that. So there's a 1-to-1 molar ratio between CO and propionaldehyde, which means that the 1.03 times 10 to the minus 3 moles of CO that were produced, those came from 1.03 times 10 to the minus 3 moles of propionaldehyde that reacted. And so my quantum yield is simply the number of moles that reacted divided by the number of photons absorbed. So 1.03 times 10 to the minus 3 moles that reacted divided by 1.91 times 10 to the minus 3 moles of photon absorbed. And if I plug that into my calculator, 1.03 divided by 1.91, and I come out with a quantum yield of about 0.54 for this reaction. So that's just a brief example of how we might use these concepts here, and a remembrance just that just because a photon has an energy greater than the enthalpy required for a reaction does not necessarily mean that that reaction can be driven by that photon.